Hello, this video is for Module 3, Part 2, and includes a discussion of multiple predictors in a logistic model. Okay, let's go ahead and get started then. So in the previous module, we considered a simple logistic model where we had only a single predictor variable. In this module here, we are going to consider several potential predictor variables. The example that we're going to use here is, again, the Pima Indians diabetes data set. We used this in the previous module. The files folder is here, provides the Colab document, the data set, and then the predictions from our final models here. There were several fields in this data set. Some of them have been grayed out here, and I'm not going to include those in our logistic model. We are trying to predict diabetes, and there is information about insulin intake and glucose concentration, which obviously is going to predict diabetes. But the goal here is to see which of these other predictor variables could be used to identify whether or not somebody has diabetes. And those include the number pregnancy, so it's the number of pregnancies. This is a grouping variable to indicate 5 or more or 4 or less pregnancies. Skin thickness, BMI, the high risk group. Okay, that comes from the diabetes pedigree function. So again, if that thing is greater than 1, I identified that as a high risk group. The age, and then finally the response here is just type 2 diabetes, whether or not the woman has diabetes. And that is at a binary level, yes or no here. Here's the data. It's the same data that we had again in the previous module, so I'll skip that. The goal here is to find an optimal predictive model. Okay, so what we're going to do that is to use the LEAPS package like we did for earlier in the course when we were looking at regression type problems. The LEAPS package allowed me to investigate all possible subsets of the predictor variables. There is one additional package that we're going to need to use for a logistic, and that is the bestglm package. So that uses LEAPS as the bestglm package. GLM package uses LEAPS to identify the best logistic model. When we were using LEAPS before, we had a regression situation where the metric that we used was the R-squared. We created a plot with the number of predictor variables and the R-squared, and we tried to find the value in the closest to the upper left-hand corner, if I remember correctly. The R-squared, remember, is just the correlation between the actual and the predictions. But here, the predictions are either a yes or no. So we're trying to classify observations here. So you cannot use Pearson's correlation measure then as a metric. So instead what we are going to do is use the Bayesian information criteria, or BIC, in trying to figure out what our optimal logistic model is. When we're using BIC, a lower value is better. Okay, a little bit about the implementation of the bestglm package in R, in Colab via R. It does not actually use a model structure, but what it does instead is uses a data frame where the data frame contains all the predictor variables that you would like to be considered. And then the column, the last column in that data frame, has to be your response. It actually has to be the numeric representation of that binary response variable. So that last column here has to be 1s and 0s. This isn't unique to just bestglm. There are other packages that use this structure instead of the model structure that we've been using up till this point. We're going to again have to specify the family as binomial because we have a binary response variable. And then finally the IC, which is the information criteria, is just the criteria that you're using to determine your optimal model. And here that's going to be specified as BIC. When you run this code in Google Colab, what you get is a table, or one of the things you get is a table that is returned. Here, this contains all of the potential predictor variables. They're either true or false here. So the first row of this table is for the first model. BMI was in this model. I have that highlighted, and age was in that model. When I had BMI and age in this model, my BIC value was 552.3. If I look at a second model, and this model included high risk group in it, my BIC went up a little bit to 553.4. The third model in this table is going to use the number pregnancy group there as one of the variables. It's going to use BMI as one of the others and age as one of, so it looks like it switched or traded high risk group for number pregnancy group. When it did that, the BIC jumped up about 4 units there. So in looking at this table, I would say that there's 2 potential models that should be investigated further. The one that has the best BIC value here, which is the 2 predictor model, has 2 terms in it, that being BMI and age. And then a second model that I'm going to call 3 terms that has age in it, has BMI in it, and then it has the high risk group in it. So these 2 BIC values are pretty close to one another, so I'm going to consider both the 2-term model and the 3-term model here. These I'm not going to include or discuss any further. So here's those 2 models. The 2-term model just has age and BMI in it, and the 3-term model has age, BMI, and high risk group in it. Here's the output that we get from the 2-term model. Here's my estimates, which those are probably the most important thing here, just because those are used to create my predictive probabilities. My Z values, we'll talk about that in a minute here. We can use those for variable importance. There is another metric that is dumped out here by Colab via R, and that's the AIC. The AIC is Aiki's information criteria, which is just an alternative criteria to using the BIC up here. So I could have used AIC as well, but I just chose to use BIC. I think BIC maybe is a little bit more common in practice. We want the AIC to be small as well. So here is the 3-term logistic model. You can see that it has age, BMI, and this high risk group variable. That was a yes-no type variable. So that is an indicator here. Right, so when the model is being constructed, I had to create an indicator variable for that particular predictor variable. So just some observations. Let's go ahead and look at the coefficients for age and BMI and also high risk group, I guess, are all positive. So that means as age increases, then the predicted probability of getting diabetes increases. As BMI increases, again, this is positive here, that indicates that the predicted probability of getting diabetes increases. When I look at the high risk group, when I'm in the yes category here, so the label here has yes on it, so the predicted probability increases when I am in the high risk group. Now, one thing that you need to be careful about here in interpreting these estimates is it does not increase by 8.84. Remember, there's a nonlinear transformation that actually happens in order to get the probabilities between 0 and 1. So you cannot say in a logistic model that when the age increases by 1, the predicted probability goes up by 0.06. That is not true at all in a logistic model. Here I'm just looking at the sign of these, and these are all positive, which means that as age increases, predicted probability increases, etc., like I've talked about. There are the Z values over here. You can use those, use the absolute value of those to determine variable importance. So here you can see age is going to be the most important predictor variable in this model, BMI next, and then the high risk group is at about 2.25. These are all larger than 2 or 1.5 maybe if you want to use that. So these are all important predictive variables in determining whether or not somebody has diabetes. Here's the variable importance plot. Again, the y-axis on here is just those absolute z-values. Let's talk a little bit about understanding the effect of the predictor variables, and I'm going to do this for the 3 variable model here. Okay, so the estimates here, negative 5.99, 0.06, 0.09, 0.84, just go into this equation, okay, this logistic equation here. Now the left-hand side of this is not the predicted probability, but it's a function of that predicted probability. As I said, the high-risk group here is an indicator variable, so that's going to be set to 1 when you are in the high-risk group. It's going to be set to 0 when you're not in the high-risk group. Here's the equation for the predictive probabilities. And to get a predictive probability, so let's just go ahead and do one here as an example. Suppose I have a 50-year-old woman who has a BMI level of 30 and is not in the high-risk group. So what I'm going to do there then, let me blow this up a little bit for you, is I'm just going to plug in 50 into this equation for her age. I'm going to plug in 30 into the equation for BMI, and I'm going to plug in 0 here because she's not in the high-risk group. All this ugly math comes down to about a 49% chance that she has diabetes. So for this particular woman, the predictive probability is going to be 0.4888. Let's just look at some different scenarios here. So this first one is a 50-year-old woman with a BMI 30 not in the high-risk group. We just said that the predicted probability is about 49%. What happens if that same age, same BMI, but this lady was actually in the high-risk group? Well, her predicted probability is going to increase by about 20% there. So given her age and BMI, being in that high-risk group increases her predicted probability quite a bit. How about the comparison between C and D here? Here I have, what did I change here? It looks like I changed the age. So woman C has a 50 age, 30 BMI, not in the high-risk group. Woman D here is a 60-year-old, has the same BMI, not in the high-risk group. Predicted probability goes from 49% up to 64%. So there's about a 15% increase there when I increase the age by 10 units, or 10 years here. Comparison between E and F is just changing the BMI going from 20 to 30, and you can see that I increased the predicted probability there by 23%. There are other interpretations that can be done for these predictor variables, and that has to do with the odds ratios. That is not covered in this course, but oftentimes odds ratios are discussed when you are trying to understand the effect of the logistic models. Here, I'm really just concerned about trying to get these predicted probabilities, so I'm not going to go into a discussion of the odds ratios that could be computed from this model. Let's talk a little bit about the visual inspection, I guess. What I have labeled here is just visually what is happening with this predictive probability equation. This equation right here has age in it, which is continuous. It's a number. Has BMI in it, which is continuous. It's a number. And it has high-risk group, which is a dummy variable, either 1 or 0, representing yes or no. The result from this model, or from this equation, so where's my equation at? Right here. This equation actually produces a surface in 3-dimensional space. This surface has age as one of its inputs. It has BMI as another input, and the outcome is the predicted probability. Now I actually get 2 surfaces because the high-risk group is a dummy variable, and what that does is it creates 2 separate surfaces. Unfortunately, I can't move this surface around and let you kind of look at it from different perspectives in Google Colab. But what I did is created a video here of just moving the surface around. I did that in a different software package that allowed me to do that more easily. So I'll let you watch that video, It'll just, again, show you kind of some of the different perspectives on what happens when I look at this surface from different, like I said, different perspectives there. You can reduce your 3D surface down to simple graphs here in two dimensions, but you're going to have to, so if I want to look at the effect of age on the predicted probability of having diabetes, I have to set the BMI at a certain level. So here I'm setting the BMI to be 30. And then I'm able to plot these two curves. The green curve here, again, is for high-risk no group, and the blue curve is for high-risk yes group. So here you're looking at the effect here of being in the high-risk group. Right, you can see that the predicted probability goes up by about 20%. And that's what we had when we were looking at this comparison between A and B here. Person A and person B, the only difference between them was whether or not they're in the high-risk group. So that's kind of that jump that I see between these two curves. Now that jump that I see is not consistent because this is a nonlinear transformation of that function. So over here, when the age is really high, the impact of being in the high-risk group is less. Okay, because age is kind of taken over that predicted, that is causing the predicted probabilities to be quite high. The graph on the right is looking at the effect of BMI. Again, I have to set the age. If I want a two-dimensional view of this, I need to set the age at some number, hold it constant at some value, and here it looks like I set it at 60. So BMI definitely has an impact on whether or not somebody is going to end up with diabetes, and also age certainly has an impact. If these curves were fairly flat, then that would mean that that predictor variable does not have an impact. Now, this is an optimal model according to the BIC criteria, so I would not expect to see curves that are close to flat, because that would not be an optimal model. Getting the predicted probabilities, I can do that with either the two-term logistic model, or I can do that with the three-term logistic model. Recall that the two-term logistic model just had age and BMI in it. The three-term had age, BMI, and high-risk group. These functions here give me a probability between 0 and 1, right? That's what this y-axis is here. These are always going to be between 0 and 1. I then, when I go to classify the observations, I have to decide what threshold to use. So if I use a 50% threshold here, so let's go across here at 50%, then anybody that is above that 50% probability is going to be classified as having diabetes, and anybody that's below that will be classified as not having diabetes. So these younger people here will tend not to have diabetes, and the older people will tend to have diabetes. Okay, so that's the idea of that threshold again. These here, well, let's just look at this. This is the BMI, high risk, age numbers. The predicted probability from the two-term model. Okay, so all I did there, or all the computer did, I didn't do this, but I plugged in 33.6, no, so that'd be a 0, and age 50 into this model up here. When I do that, my theta hat value is 0.5978. If I'm using a 50% threshold, I need to check if this value is above 0.50, and it is. So I'm going to classify that person as having diabetes. I can do the same thing here with the predicted probability three-term model. So there I would have to plug in 33.6, the no, and 50 again, and I'd end up with a predicted probability of 0.5764, which is pretty close to what I had with the two-term model. I think I misspoke earlier. When I was doing a two-term model, all I need here is the BMI and the age. I don't need the high-risk group in that two-term model. But notice these predicted probabilities are really pretty close here. Okay, so this person, and that's true all the way down. The results here from the two-term model and the three-term model are pretty close. Notice the predicted probability here is 0.18. That's less than 0.5. So that's going to be predicted as no, right? And we're going to do that all the way down. And here we're going to do for the three-term, we're obviously going to use the probabilities from the three-term. And how good the model is doing is just we need to investigate the predicted class versus the actual type 2 diabetes. So this column here against this column here. And that's what the confusion table does. It just looks at these values against these values. So let's go ahead and look at the confusion table for a two-term logistic. Here you have, again, 285 people that did not have diabetes, and my model predicted them not to have diabetes, so that's pretty good. I have 62 here where the model predicted them to have diabetes, and they actually did have diabetes. So if I do a calculation for accuracy, I'm going to take this 285 and this, I'm going to take this 285 and that 62, not able to highlight both of those at the same time. 285 and the 62 are the ones that I got correct, so that's how I'm going to compute my accuracy. There's 490 people in this model that were used in this model, so 285 plus 62 is 347. 347 divided by 490 is about 70%. If I have an accuracy rate of about 70%, then I'm going to have a misclassification rate of about 30%. So these are just opposites of one another. When I go to the three-term logistic, my accuracy jumps up a little bit to 71.2%. And my misclassification rate actually goes down. One thing that I'll mention about this model is that the misclassification rate for this Pima Indian data set is actually pretty high. A lot of times when we do classification problems, this misclassification rate gets down to 5% or 3%. So when we do this, I don't want to give you the impression that we can only be right about 70% of the time with these models. It's just this particular data set that I've chose to use to construct these notes only has an accuracy level of about 70%. In addition to the accuracy and misclassification metrics, we can worry about or look at the area under the curve. Here's the gray there is a little bit harder to see. That's the two-term model, and the black is the three-term model. These two ROC curves are very similar to one another. The area under the curve, again, we want that to be as large as possible. A model where I'm just simply guessing is going to have an area under the curve of 0.5. So again, that's kind of my baseline reference here. And you can see that the three-term model does slightly better than the two-term model here. I can also determine an optimal threshold. The optimal threshold is going to be different for different models, obviously. So for the two-term logistic, my optimal threshold was 0.33. And here's what my confusion table looks like for that situation. And then my three-term the optimal is at 0.35. Now I want you to look here at let's go ahead and look at the 51 and the 115. So when I use a optimal threshold here, okay, I had 115 here that were predicted to have diabetes that actually did have diabetes. All right, so maybe let's just look at that 115 first. When I use the default threshold, that value was only 62. So again, this is those that actually have diabetes. How many did I predict to have diabetes? That was 62 here. Okay, so what I'm thinking here in my head is the true positive rate. The true positive rate, or what's called the sensitivity, is going to be 62 divided by the total number of people that have diabetes. When I look at my optimal threshold, that's going to be 115 divided by the total number of people that have diabetes. So my sensitivity, or the more easier name to remember, is the true positive rate, is going to go up a lot when I use this optimal threshold. What is also going to happen, though, is that I am going to increase my false positive rate as well. So here I had 39 that I said did have diabetes out of the 285 plus the 39 there. So if I make it easier to say people have diabetes, then my false positive rate's going to go up as well. So here I have 39 in that cell, and that's jumping up to 105. It's actually jumping up quite a bit. So when I increase the threshold, or reduce the threshold, excuse me, to 0.33, when I'm using this optimal threshold, I do certainly increase my true positive rate, but I'm also increasing my false positive rate. As we talked before, you're going to need to consider the balance that's necessary between those two types of errors that you're making when you are modeling, or the balance between true positive rate and the false positive rate. So here is a kind of a table that summarizes all the information regarding the metrics from these different models. This is a two-term model here with using the default threshold. Here's the three-term model using default threshold. Then I have the two-term model using an optimal threshold, and obviously three-term using its optimal threshold. So if you're just worried about accuracy, then the model that you're going to want to use is the three-term model here with age, BMI, and high-risk group. That did have, if I remember correctly, the second lowest BIC. It had I think it was the lower AIC, if I remember correctly, and it has the highest accuracy. Now, it is not optimal in the sense of the true positive rate. And the true positive rate, again, is of those that have diabetes, were you able to correctly predict that they had diabetes? And I was only able to do that 40% of the time here with that model. If you want to maximize your true positive rate, then the model that you should use is a two-term model using its optimal threshold value of 0.33. Now, we do lose a little bit in terms of the accuracy, but we gain a lot in the true positive rate. Okay, just some final comments here. I think we hit most of these. So this comment here is that oftentimes we can get our misclassification rates down to less than 10%. Again, the Pima Indian data set isn't real great in terms of its misclassification rates and accuracy rates. And then here I just strongly encourage you to think about the metrics more holistically here when you're doing logistic regression. It'd be really bad to just decide that the best model is the one that has the highest accuracy, because that one does not produce a model that has the highest true positive rate. Okay, so I'll be honest with you, modeling and doing logistic modeling, we start to have an element of the art of doing modeling and not just strictly what produces the highest metric. When we did regression type problems, usually the highest metric just kind of wins out. The R-squared just kind of wins out. But when we're doing logistic modeling, you got to worry about what kind of metric are you going to use and what does that metric mean to my problem. That really comes into play more when you're doing logistic modeling. The task here just has you answer, I think it's 4 questions, okay, regarding some of these models that I created. That's all I have then for this video. Thanks for watching. Have a good day. Bye.